Hey, welcome. Today, we're diving into the really cool world of non-traditional machining. We're going to meet a trio of super powerful processes that can shape materials in ways that honestly seem almost impossible. So let's get right into it. So let me just start with a question. How in the world would you cut through 2 inches of solid steel using just water? Or how about delicately etching a pattern on glass using a stream of air? I know, it sounds like something straight out of science fiction, but believe it or not, this is the reality of modern manufacturing. Now, we're not talking about your everyday workshop tools here. When you're dealing with materials that are way too hard or too brittle, or maybe just too delicate for a standard lathe or milling machine, you have to get creative. You need a completely different approach. You have to call in the specialists, and that's exactly who we're going to meet today. We're stepping beyond the conventional stuff to look at 3 incredible non-traditional methods that all run on raw mechanical energy. You can think of them as the elite special forces of the manufacturing world. All right, let's meet our first operator. First up, abrasive jet machining, or AJM for short. Now, this is the precision artist of the group. It specializes in all the fine, delicate work, especially on brittle materials. So, how does this thing work? Well, the core idea is basically mechanical erosion, but it's supercharged and precisely controlled. I want you to picture a tiny, focused sandstorm. You've got a high-velocity stream of gas, something like air or nitrogen, and it's carrying these teeny tiny abrasive particles. When that stream hits a brittle surface, like glass or a ceramic, it chips away material by creating thousands of tiny microfractures. It is literally erosion on demand. And the setup, it's actually brilliantly simple. First, you get a high-pressure gas supply. That gas flows into a mixing chamber, and in there, it picks up a very fine abrasive powder. Then, this powerful mixture is blasted through a nozzle, which has to be made of something incredibly hard, like tungsten carbide, just to survive, and it's aimed right at the workpiece. That little gap between the nozzle and the material is totally critical for getting the cut just right. Okay, so what's AJM really good for? Well, it's perfect for those delicate jobs, like putting a frosted finish on glass or cleaning tiny burrs off complex medical implants without damaging them. But it's not a powerhouse. The rate at which it removes material is pretty slow, and you have to be really careful to contain all that abrasive dust. All right, time to meet our second specialist, abrasive water jet machining, or AWJM. If AJM was the artist, I want you to think of AWJM as a heavy-duty demolition expert who also happens to be a surgeon. The principle here is kind of similar to AJM, but we're swapping out the gas for water and just cranking the power way, way up. And this is where it gets really smart. It all starts with ultra-high pressure water. As that water shoots out of a tiny opening, it creates a vacuum. This vacuum then sucks in abrasive particles, usually a hard mineral like garnet, and focuses them all into one incredibly powerful cutting stream. And when I say ultra-high pressure, I am not kidding. We're talking up to 4,000 bar. That is hundreds and hundreds of times more powerful than the pressure washer you might have at home. It's just an immense amount of focused energy. And that incredible pressure is what transforms a simple stream of water and sand into what our source material calls a deadly precise cutting beam. It's like taking a force of nature, taming it, and focusing it into a tool. The machinery itself really reflects this power. It all starts with this massive ultra-high pressure pump. From there, the water is piped to the mixing head where it meets the abrasive. Then, after it slices right through the material, that unbelievably powerful jet has to be stopped safely. And that's the job of the catcher tank. It's just this huge basin of water that absorbs all the jet's remaining energy. You know, the biggest win here is its versatility. AWJM can cut through pretty much anything, from titanium for aerospace parts to thick granite for countertops, and it does it all without generating any heat. Now, this is a huge deal because heat can warp a material or change its properties. The trade-off? Well, it's extremely noisy, and keeping that high-pressure pump in working order takes a whole lot of maintenance. And that brings us to our third and final specialist, ultrasonic machining, or USM. Now, this one is completely different from the other two. It doesn't use a jet at all. Nope. This one uses vibration. The principle behind USM is just fantastic. A tool vibrates at an ultrasonic frequency. We're talking around 20,000 times every single second, way beyond what a human can hear. Now, this vibrating tool doesn't actually cut the material directly. Instead, it hammers these tiny, hard, abrasive grains against the workpiece, chipping away material bit by bit. The source material had the perfect analogy for this. It's like a microscopic jackhammer. So let's break down how it works. It starts with something called a transducer, which turns electricity into these high-frequency vibrations. Then, a component they call a horn concentrates and amplifies that vibrational energy, focusing it down into the tool. Finally, the vibrating tool is lowered into an abrasive slurry, which is just a mix of water and super hard particles. And that slurry is what transfers that rapid-fire hammering action to the workpiece. USM is the absolute master of machining extremely hard and brittle materials. We're talking things like quartz, glass, and those advanced ceramics you find in electronics or even in dental crowns. And it does all this without creating any heat or chemical changes, which is absolutely vital for materials this sensitive. So what are its limits? Well, it's a very slow process. And because the tool itself is doing all that hammering, it also wears down over time. Okay, so we've met our three specialists: the artist, the demolition expert/surgeon, and the microscopic jackhammer. Now, let's put them all side by side to really see how they stack up. This table makes the choice crystal clear. You can see how the medium, whether it's air, water, or a slurry, directly relates to the kind of material you're working with. AJM's gentle airstream is for thin, brittle parts. AWJM's powerful water jet is what you call for thick, hard materials. And USM's slurry? That's the specialist for the super hard and brittle stuff. And notice this: if you need the absolute best, most pristine surface finish for something like a precision lens, USM is the clear winner. And this right here is really the key takeaway. These methods aren't meant to replace the trusty old conventional tools. They exist to push the boundaries of what's possible in manufacturing, to create these complex shapes in really difficult materials that would otherwise be impossible to make. These are the tools for building the future. So that leaves us with one final thought. With tools that can literally cut steel with water and carve ceramics with sound waves, what impossible components are going to be built next? It is pretty exciting to think about. Thanks for joining me on this deep dive.